Welcome all. Our this week's discussion topic is frequency response of op-amp. Content. So first we'll discuss what is frequency response, then the gain bandwidth product, noise gain, and some related mathematical examples, and finally the absolute maximum ratings. Frequency response of op-amp. So this topic is about what are the responses from a op-amp, from an op-amp, that when we give some inputs, then what will be the output frequency and how it changes, and is it constant or it is something like sloping things. So for there are two things that we can say. If there is no coupling things or any lead network, something like capacitors, then the gain will be flat. Okay, it is not something more high. It is something from midband down to some DC, so it will not fluctuate heavily. And another thing that is which will if for high frequency devices, it is something roll off, that is, it is something sloping. So for general purpose of op-amps, the high frequency response may be determined through gain bandwidth, that is a parameter of to determine the high frequency response, and that is often called ZBW, that is gain bandwidth. Gain bandwidth product. So you can see that in the figure, this is a general shape of output response or frequency response of an op-amp, but it may vary. It may vary for the different model of op-amp, and the output values may also vary. But this shape will normally the something like this one. So in first portion there is a constant part. So for less frequency, the constant gain, something here you see that 100 dB, and then it started to roll off slope. That's been from 10 Hz it started to roll off, and when the frequency is increasing and gain is decreasing, and this decade roll off slope is 20 dB per decade. So in this way it is having the decreasing value for any devices. In general, I say that it is for general uh, curve. For model to model it may vary, the value may vary, and this it has a break frequency, that is FC, when the constant term is started to roll off slope. So from this 10 Hz, this one is the break frequency for this op-amp, for this fixed model op-amp. And then that could be determined by a single capacitor, and that is called the compensation capacitor. The position of a compensation capacitor is something in this figure it is shown here. This one is the capacitor. So when the capacitor value is very low, then the critical frequency is also very low. Often the range is from 10 to 100 Hertz, only Hertz. But when the load capacitance are much higher, then the frequency is also higher, something like more than 1 megahertz. And as a result, a constant 20 dB per decade roll-off is maintained from the break frequency up to very high frequency. That's when the slope is from the break frequency, it is it maintained almost 20 dB per decade. Comparison of open loop and closed loop responses. So this is the diagram. One is for open loop, the red one, and the green one is for closed loop. So this is the response, and you see the closed loop response at a time it touches the open loop. That's when it's the gain of closed loop is in a middle position, but at a position it will start to flow something like the open loop in this position. But the open loop is start in the gain is very high on that position when the frequency is very low, and after some points it started to break frequency. After the break frequency started to roll off, it has a decade. But for closed loop, the roll off started very late. That's been after very high frequencies started to roll off. And for the inverting and non-inverting voltage amplifier, we can determine ZBW. That's been the gain bandwidth and also the break frequency by using the equation F2 is equals to gain bandwidth divided by gain. That means it is a noise gain. It is not exactly the gain, but it is something like noise gain. Noise gain. So this is not the ordinary voltage gain. It is called a noise gain when actually makes the result a bit more accurate. And this is with the feedback of non-ideal cases when there is some use of noises and feedback effects and circuit imperfections. So it counts that things into noise gain. So this is not the same things for ordinary voltage gain, but for inverting and for non-inverting voltage amplifier, the noise gain is same, and the equation is A noise gain. That's when A means the gain, A noise equals to 1 plus Rf by Ri. We know that for inverting and non-inverting the normal voltage gain is different, but for noise gain, when we want to calculate the noise gain, for both of the cases it is 1 plus Rf by Ri. An example, using a 741 op-amp, what is the upper break frequency for a non-inverting amplifier with a gain of 20 dB or 10? So 20 dB can be converted into 10, or from 10 it can be converted from 20 dB. So two different things, but we can use the equation to convert 20 decibel into a normal unitless voltage gain, that is 10. So the question may have only the 20 dB or may have only the 10, and you can swap between these two. So how to do it? A 741 datasheet. If we see the datasheet of a 741 op-amp, the typical gain bandwidth ZBW is 1 MHz. So it is in general case we can use these things. The noise gain for a non-inverting amplifier is the same as its ordinary gain. You know that A noise is same for the ordinary gain, that is non-inverting case 1 plus Rf by Ri. So both is same for non-inverting amplifier noise gain and ordinary gain. So you can use F2, that's the break frequency F2 equals to GBW divided by A noise. So A noise is 10. We need to give the value of without decimal. We need to convert it into normal gain value, that is 10, and ZBW is 1 MHz. So if we calculate, that is 100 kHz. So 100 kHz is the break frequency, actually upper break frequency. So if we want to draw the curve, so it will start from 10 in general, from normal 10 Hz to 100 kHz, and then after 100 kHz till 100 kHz it is constant gain, okay, and after 100 kHz it is called break frequency 100 kHz, and then it started to roll up at 20 dB per decade. That means the slope will start from here after 100 kHz. That's why 100 kHz is called the break frequency. Another example, sketch the frequency response of the circuit in figure below. So one circuit is given and we need to draw the output frequency response of this circuit. So first you need to understand what type of circuit it is, and you see that this is a inverting amplifier. So one feedback resistance is given 10k and input resistance is given 2k, and there is a voltage source here. So for this inverting amplifier, we know that normal voltage gain is minus Rf by Ri. So normal voltage AV, that is minus Rf by Ri inverting. So we can calculate Rf 10k and divided by Ri 2k. So answer is minus 5. So this is minus 5 in voltage gain, but we need to convert it in decibel, and the equation is dB equals to 20 log V1 by V2. V1 by V2 is the gain. So we can use the calculator and we can find that it is 14 dB, and this 14 dB is actually the gain that will draw in the its case in frequency response curve. That will be the highest gain. Okay, now we want to calculate the noise gain, and you know that noise gain is 1 plus Rf by Ri, and this noise gain is same for both inverting and non-inverting. So if we put the values, we get the noise gain is 6. So why we need the noise gain? Because we want to calculate the break frequency, that is F2, and there we need to use the noise frequency. So from the data sheet, we know that I said previously that the ZBW gain bandwidth must be 1 megahertz for a 741 op-amp, and the A noise is 6 given, so F2 is equals to 167 kilohertz. So this is the break frequency, because we need all the data to draw to sketch the frequency response curve. So here the resulting gain board plot here. So it is also called board plot or the frequency response curve, and you see that the highest gain is 14 dB that we calculated. So it start from here until 167 kilo hertz. It is constant. Then after 167 kilohertz, it started to slope, and that is still 1 megahertz. So in this way, you can draw the frequency response curve of an op-amp. Example, the question is determine the minimum acceptable F unity, frequency of unity, for the circuit of figure if response should extend to at least 50 kilohertz. 50 kilohertz, this value is actually the break frequency. It is constant till this, and the circuit is a non-inverting amplifier. You see, 20 kilo is the RF and 500 kilo is the RI. Okay, so to find out the F unity, you need to find out the F unity frequency, and the equation is F unity is equals to A noise, that's mean gain, into break frequency. So to the gain is we need to calculate the gain, and the break frequency is given 50 kilohertz. So gain is noise gain, that is A noise, is equals to 1 plus Rf by Ri. So if we put the values, then the result is 41. So this 41 and 50 kilohertz here, if we multiply, so the result is unity gain is 2.05 megahertz. So this is the answer of F unity. Example, assuming that all stages in figure use 741 op-amps, what is the system gain and upper break frequency? So one circuit is given in this figure, and that is a combinational circuit. 3 op-amps is connected with each other, and we need to find the system gain, that's mean the total system gain of this circuit, and the upper break frequency of this total circuit. So you see that 3 op-amp is connected as the voltage source is connected in plus terminal, this terminal here. Feedback resistance is here, and also the input resistance. Now the second op-amp is connected with the output of the first op-amp. So here also the feedback resistance RF 20 kilo and input resistance 10k, and the input connected with the inverting terminal. So first one was non-inverting, second one is inverting, and third one is again the non-inverting terminal. It is connected, and it has also the feedback resistor RF, that is 12k, and also the input resistance 4k. So we need to find the system gain. So for the system gain, that's mean total output gain, we need to find the individual gain. So if we can calculate the individual gain of each op-amp, then we can multiply with these three gain, and then we can find the total system gain. And for upper break frequency, we need to find break frequency for all the three op-amps. So for three different stages, we will calculate the break frequency, then we will see which one is a lower value. That lower value will be the total system break frequency. So for solution, we will start with the stage 1, that's been the first op-amp, this one. And in this circuit, as it is the non-inverting terminal, so the voltage gain, the normal equation, you know that AV, gain voltage, is equals to 1 plus RF by RI. So if we put the value 14 kilo ohm and 2 kilo ohm RI, and the result is 8 unit less, it is a gain value. So this one is 8. Next we need to find the noise gain to find the break frequency. Now the gain of noise, that's the noise gain of first stage, and you know the equation is 1 plus RF by RI. So if you put the value, then the noise gain is 8. So for non-inverting inverting terminal, the noise gain and normal gain is same. And now we can find the break frequency, that is F2. So this is F2 is equals to gain bandwidth divided by noise gain. So if you put the value 1 megahertz divided by 8, so it will be 125 kilohertz. Now the next stage, that's the second stage. In second stage, we had the op-amp connected in inverting terminal. So the voltage gain AV is equals to minus RF by RI, and the value minus 20k RF, and RI is 10k. So the result is minus 2. So this is the voltage gain of second op-amp. Now the noise gain of second op-amp is 1 plus RF by RI. So equation is different. It is not like the RF by RI. It is 1 plus RF by RI for all the cases. So the result is 3. Noise gain is 3. Now the break frequency of this second stage, F2 equals to same equation, gain bandwidth divided by noise gain. So 1 megahertz by default from the data sheet, and divided by the 3 noise gain. So we must put the value of noise gain, not the voltage gain, 3. So the equation F2 is equals to 333 kilohertz. So this is the break frequency of second part. And now the third stage, stage 3. So voltage gain 1 plus RF by RI, because this is connected in non-inverting terminal, and voltage gain is, so if we put the value, it is calculated to 4. So voltage gain AV equals to 4. Then the noise gain is equals to 1 plus RF by RI. So same value, so it is also 4. And the last stage break frequency is F2 equals to same equation, gain bandwidth divided by noise gain, and the result is 1 megahertz divided by 4, so 250 kilohertz. So if we want to calculate the total system gain, so that is the equation AV equals to multiplication of all the individual gain. So 8 into minus 2 into 4, and you must remember that this is the voltage gain, not the noise gain. So the result is minus 64. That is the gain. And we need to find the break frequency, upper break frequency, and we need to see that and the system what is the lowest break frequency, and that is in a fast stage that was 125. So this is the dominant distance and the value is 125 the break frequency. So that is the result of the system. Absolute maximum ratings. So the table shows the absolute maximum ratings of an op-amp. So it is in general cases what are the supply voltage or in power dissipations or input voltage, and this is for 741 op-amp 741 model. So we cannot exceed these values. It must be in between this. So you see that the supply voltage is in between plus minus 22 volt. Normally it is we supply normally 18 volt to an op-amp. Internal power dissipation is 500 milliwatt, and differential input voltage plus minus 30 volt. That's when two input voltage, and for that two input voltage the differential will be 30 volt, and one individual input voltage should be plus minus in between 15 volt. An example: determine the current draw from a dual power supply of plus minus 12 volt if the IC dissipates 500 milliwatt. So we need to find the current value, and the power supply is given, and also the voltage, that is plus minus 12. So we know that power equation P equals to VI, and here we assume that each supply provides half the total power. So total power is 500 milliwatt, so half will be 250 milliwatt. So P equals to VI, P equals to 250 milliwatt for one portion, because it has the dual supply. So one portion 250 milliwatt, and VI voltage 12 volt, and current we need to find the current, and that current is equals to I equals to 250 milliwatt divided by 12 volt, and so if we find the result, it is 20.83 milliampere. So this is the current rating of this system. Self-directed learning. The question is how to define upper break frequency. So please follow the forum and quiz of this week, and that's all for this week. Thank you.